All right, good afternoon, everyone. So we're going to get into our discussion of the support vector machine today. So there's a number of details to kind of swallow here, so please try to pay attention. So just to sort of review what we did last time, we were studying the geometry of linear classification, and all these things we can observe are important ingredients in our support vector machine. So here we have the decision boundary that in this case is separating the red samples from the blue samples. And we know that the equation for, and this is just a simple case where we have two features, x1 and x2. But in the general case where you stack all your features into x, then the equation for the points along that line is this. It's the set of x such that b plus x transpose w equals 0. And remember that this thing here, this is our score that we call z. This is like the real valued quantity that comes out of the classifier that tells us for this test sample x how confident we are that the label is 1 or not 1. So as z gets larger, we're more confident that the label equals 1. And as z gets more and more negative, we're confident that the label is not 1. So either 0 or minus 1, whichever we use. And when it's at exactly 0, then we just have no idea whether the label is 1 or minus 1. That's the point of least confidence. It's when we're here. Okay, so the first thing that we noticed is that the hyperplane is orthogonal to our weight vector w. So our weight vector w is here, and what we did is we looked at 2 points on the hyperplane. We drew a line between them, so that is definitely a line that is parallel to the hyperplane. And we know that for each of the points, x1 and x2 on that line, this equation holds true. Then we subtracted those two equations from each other. The b's canceled out, and we got this. So this tells us that x1 minus x2, which is something parallel to this line, is orthogonal to the inner product of 0 means it's orthogonal to w. So we get this right angle. Okay. Another thing we didn't mention last time, but it's something good to notice right now, is we can see pretty easily what the intercept values are going to be. So imagine that we are somewhere on the x1 axis. That means all the other variables, like x2 and all the other ones if we have them, are all equal to 0, right, when we're along this axis. So if that's the case, and we want to know where does this boundary cross that axis, we just look at this equation, but we set all the other x's equal to 0, at which point this becomes b plus x1, w1 equals 0, right? If I'm looking at this point right here along the x1 axis. And if we rearrange that equation, you can see that x1 must be this value minus b divided by w1. Right? So if you want to know where does the boundary cross this axis, it's just minus b over w1. That's where it crosses the x1 axis. Similarly, it crosses the x2 axis at minus b over w2. Or for any j, it crosses the xj axis at minus b over wj. Okay, so that's another little thing we can notice in the figure. Right. Any questions on that? Okay, so another important thing that will lead us directly to our support vector machine is we'd like to characterize the distance between any training point, xi, and the boundary. So we want to measure, the distance from here to there. And so when we measure distance from a point to a plane, essentially we want to go right in the direction towards that plane, right? Like if I want to measure the distance from xi to the plane, I don't want to be measuring this distance, which is not orthogonal to the plane. I want to be measuring the distance, the closest distance to the plane, which means there's an there's a right angle here. Okay, so what we can do is we know the direction. This direction is in the same direction as W. So essentially, I want to travel in the same direction of W as far as I need to get to the boundary. And we know that when we're at the boundary, this equation holds. Okay, so that's the method we're going to use to figure out the distance. And there's one complicating factor about W is that we know that the direction is perpendicular to the boundary, but we don't know the norm on W. The norm on W could be big or could be large. So to remove that ambiguity, we're going to focus on this new vector W over the norm of W. This is a vector that has the same direction of W but is unit length, unit norm, right? So this is what we call the unit vector in the direction of W. And so if I want to measure how far xi is to this plane, I need to figure out what is the value gamma I such that xi minus gamma I this. So this has a total norm or length of gamma I. I want to know what is the gamma I that makes this obey this equation. This new point, I plug it in here, and this is the equation that must hold true if I'm on the boundary. So that's how we do this. We basically plug this into here and solve for gamma I. Is that part clear? That's what we do here. So this is the equation for a point on the line. This is starting at x and moving a distance of gamma I in this unit direction, W. And I know that this must hold when gamma I is properly selected, and it puts me right on that boundary. Is everybody okay with this? The rest is just a little bit of algebra. But this is the main idea. Okay, so we're trying to figure out how far do I have to move in this unit direction to place me on the line, and that's going to be the distance from this training point to the boundary. And that's an important thing when you classify, right? Training points that are close to the boundary, those are the difficult ones to determine. The ones that are far from the boundary, those are easy to classify. So this distance is going to tell us something about how difficult a training point is to classify. Okay, so any questions on why we're doing this? Is this okay? So we have this, and we want to basically solve for gamma I. So it's not too difficult. So let's just do this multiplication. So we have xi transpose w. That's going to be here. And then for this next term here, we have w transpose w. Well, remember that w transpose w is the squared Euclidean norm of w. So that squared Euclidean norm, we're going to divide that by the unsquared Euclidean norm, and that's just going to leave us with the unsquared Euclidean norm. So this term here reduces to this. And we're almost done. Now we know that 0 equals this. So to figure out, we can easily figure out what gamma I is, just rearrange, and this is what gamma I is. Okay, so if you have a training point xi, and you want to know how close that point is to your classification boundary, you basically plug it into this equation, and you get this distance. Any questions so far? So one important thing about this distance is this is a signed distance. So usually when we think of distance, we think of a positive quantity. Right? But this quantity can be positive or negative, depending on the signs of the b's and the weights w. And what that signifies is that when you're on the side of the hyperplane that correspond to the ones class, that's going to give you a positive distance. And when you're on the side of the hyperplane that corresponds to the non-ones class, that's going to give you a negative distance. So that's what we mean by a signed distance from a point to the hyperplane. Okay, so this is going to be an important thing we're going to use on the next slide. Are there any questions about that? All right, so there's just one more thing to discuss on this slide, which is an interesting thing. If you notice, if you imagine scaling both the intercept B and the weights by the same number alpha, and let's just assume that alpha is positive, what changes about this picture? So do the intercepts change? No. Nothing changes. So if you think about the classifier really as just this boundary, because if I tell you the boundary, you know exactly how classification is going to happen, right? So if the classifier is just the boundary, you can, and also the classifier is completely parameterized by B and W, then it's interesting to know that if you scale B and W both by an arbitrary positive number alpha, you get essentially the same boundary, the same classifier. So we're going to call these two classifiers, the scaled one and the non-scaled one, equivalent. The reason we don't want to choose a negative alpha here is that would actually change, if you scaled B and W by -1, that would actually change the sign of the distance. So we don't want to do that, but any positive scaling doesn't really change our classifier. It may change the value of a loss function like our logistic regression loss. That definitely changes if you scale B and W, but the actual classifier you get at the end of the day has not changed. So I think you've seen problems like that in some of the homework assignments from what I remember, scaling weights and seeing what happens. Okay, so there's basically the main points here. We have orthogonality with W and the boundary. We know what the intercepts are in the feature space, and we have this notion of sign distance from a point to the boundary, and we have a way of computing that using B and W and the point in question. And finally, we have this equivalence that if we scale both the intercept and the weights by the same positive number, we basically get the same classifier. They're equivalent in a certain sense. Okay, any questions on anything here? Are we good to move on? Okay. So now let's review this concept of linear separability, which we talked about back in Unit 5. So in Unit 5, I think we basically explained the main idea. We didn't use any math at the time, didn't really need to. But the main idea is that if you have a data set where you have, this is a training data set, we have points from one class here, points from the other class here, and if you can find a boundary, a hyperplane, that perfectly splits this feature space such that on one side of the boundary you have training points from one class and on the other you have training points from the other class, we call that linear separable because we're basically separating this with a line, with a hyperplane. And as you can see, there's many different ways for this particular data set to be split. Here's a couple, but you can draw many more. So now we'd like to write this down mathematically, just with equations. So for this slide, just because the notation is a little cleaner, we're going to assume that our labels, y's are plus minus 1 rather than 0, 1. Okay, so we're going to say that the data, which in this case, we have samples 1 through n, the data is linearly separable if there exists some B and W that basically parameterizes the boundary and some positive number epsilon such that, now this is the score for sample I, right? Let me write that down. You can think of this as Zi, both of these, that if the label is 1, that the score for that same sample is greater or equal to this positive number. So basically the score must also be positive. If the label is positive, the score is positive. On the other hand, if the label is negative, the score is negative. That's basically how we can think about linear separability. Because remember that when you consider this hyperplane, when you write on the hyperplane, Z, the score is 0. As you go on one side, let's say that this is the ones class, you have Z is positive, and on the other side, z is negative, that would be the minus ones class. So basically, if your scores align with your labels perfectly for every point, you have a linearly separable data set. So this is how we can think about it. And we don't want to have a situation where along our boundary we have samples from both classes. If they're exactly on the boundary, then it's not really separable, right? We just need them to be a little bit off the boundary. That's why we have this positive epsilon. It pushes us just a little bit, pushes the points a little bit off the boundary for them to be linearly separable. Okay, so any questions on this? Is this making sense? Okay, so now what's nice is we can rewrite both of these just in terms of a single inequality. And you can see that by, so this is our new inequality here. And essentially, you can see that if yi is 1 in this circled inequality, you get this, right? And if yi is negative 1 down here, then you change the sign of this. But if you negate both sides of the inequality, you restore the sign on the left side, you change the sign of the inequality, and you negate this, at which point you get this. Okay, so basically this expression, when y is 1 and minus 1, gives you both of these. So this is just a nice compact way of saying the same thing as this. Okay, so this is a simpler way of stating what we mean by linear separability. And let me try to explain a little bit more about this. So again, this is the score of the zi of the ith training sample. And you can think of this multiplication by yi as like a sign correction on that score. So, in the linear separable case, these are all positive when the label is 1, and they're all negative when the label is minus 1. So by doing this sign correction, the product of yi and zi should always be positive. So this gives us kind of a unified way of looking at the quality of a score. You basically do your sign correction, multiply by yi, and then you check to see how positive it is. The more positive, the more confident you are about that point. Okay. All right, everybody with me so far? Okay, so it turns out we can simplify this farther by getting rid of the epsilon. So one way to think about this is, well, what if we just divided both sides of this inequality by epsilon? Well, epsilon is a positive number, so the inequality doesn't change directions. And what you would get is this would turn into a 1, and then both of these would be scaled by epsilon. But remember, on the previous page, we discovered that if you scale b and w identically by the same positive number, it's basically the equivalent classifier. So that's one way to think about this. So it basically says, like, you don't have to worry about this being a specific number epsilon or some positive number. You can actually fix this number at 1. And basically it means, like, if you can find some b and w such that this holds for some epsilon, then you can find a different b and w that's scaled such that this holds with epsilon equals 1. And that allows us to finally rewrite our linear separability as this nice equation here, which doesn't involve any epsilons. And it basically says there exists, that's what this backwards e is, there exists some b and w pair such that the sign corrected score is greater or equal to 1 for all your training samples I. If you can find a b and w where this holds for all I, that is basically what it means to be linearly separable. Okay, so this is going to be an important equation for us going forward. Any questions on this? Okay. So now the next step is to combine this equation with this one over here. This was our equation for the sign distance. So for example, let's imagine that we multiply left and right here by yi. Okay. So I have yi times gamma I. So this, here I have the sign distance, and now I'm correcting the sign on the sign distance. And on the right, I have this quantity which we know for linearly separable data is greater or equal to 1. So basically, all I need to do now is I just apply this inequality up here, and I can tell you that this sign-corrected distance here is greater or equal to 1 over the norm of omega for all I if the data set is separable. Right? So if the data set is separable, then all these sign-corrected signed distances are greater or equal to 1 over w for all I. We're going to give this 1 over norm of w a name. We're going to call it gamma, and we're going to give it a variable, and we're going to give it a name called the margin. And so this is finally the way of understanding this expression. The margin is basically, it's a lower bound on the minimum distance from any training point to the boundary. So let's look at the picture here on the right. So when you look at all these different points from either class, you can see that there's a certain minimum distance, here's that gamma, where there's no point that's closer to the boundary than gamma, right? They're all pushed apart a certain amount. So that's this margin. It's a lower bound on the minimum distance from any training point to the boundary. And moreover, when this data set is linearly separable, you can actually, there's, I guess you could see that you could say, well, if that gamma holds, then there's maybe even another gamma holds that's smaller. But it's more interesting to consider like the tightest lower bound or the biggest such gamma you can construct. In any case, you can get these different gammas by just looking at 1 over the norm of W. Okay, so this is why we care about this. If you think just from a practical classification standpoint, you have a data set like this, and you're asked to come up with a boundary, just visually. What kind of a boundary would you like for your classifier to work well? Would you like this boundary that's shown here, or would you instead like this boundary here? They're both separating the data, but what's not as satisfying about this red boundary? Yeah, there's some points that are really close. Okay, but then let's go deeper. So the training points are still getting classified perfectly, right? So what's the problem, really? Test data. The test data is not going to be exactly like the training data. We hope it's similar. And so if we're getting close to misclassifying on the training data, we're probably going to be misclassifying the test data. Whereas this guy is robust because this has a big margin that is pushing it away from all the training points, which allows us at test time, to have a bit of a wiggle room, or, basically we could tolerate test samples that are a little bit different than the training, but they wouldn't get misclassified. So this kind of robustness is how we get this idea of the support vector machine. It is a classifier based on finding the maximum margin, choosing the boundary so that this distance is maximum.
Does support vector machine only work if it's linearly separable?
That's a great question. We're first going to talk about a version that only works when it's linearly separable because it's easier to write down, and then we're going to fix it. Right, but that's a great question. Okay, so
But if we have a noise in our data,
well, yeah, so you always expect some difference between the test and training data, right? So what we're trying to do is we're trying to protect against the fact that we expect a difference. And so the more margin, the more room for error that we tolerate, the better we expect this to work. So if I have a small margin classifier, where the margin is the distance here and here, that classifier doesn't have much room for error. So when I have a difference in my test training, I'm more likely to get errors on the test data, even though I'm not getting errors on the training data. So that's the whole idea, is let's try to be robust. And we're going to measure robustness by the distance to the closest training sample. Another way to think about this is the training samples that are most difficult to classify are the ones closest to this boundary, right? Those are the hard ones to classify. The easy ones to classify are the ones far from the boundary. So we should not get distracted in coming up with a boundary that is using the easy samples. We should be focusing on the hard ones. That will give us a more robust boundary. So that's another idea that comes out of this way of thinking about things. Okay, so so these are the main ideas, and we're just about ready to say exactly how we're going to attack this problem, but are there any more questions so far? Okay, so again, this is our margin, gamma. We can also write it as 1 over the norm of W, and we want to maximize the margin, right? So we want to maximize 1 over the norm of W. But of course, it's that alone is not enough. We actually have to do that while at the same time making sure that all of our training samples are correctly classified. Because I could come up with, a W which is pointed this way, whose norm is maybe really tiny, so that 1 over norm of W is huge. But that's useless because it's making errors on all these samples. So I really want to do two things. I want to make sure that this equality holds for all my training samples, and I want to make this quantity, the margin, as large as possible. Okay, so that's the idea. So our approach is to make classifier robust. We're going to maximize the margin, and we're going to do this specifically by minimizing the norm of W under the linear separability constraint. Okay. Minimizing norm of W makes this part big. Okay, so writing that down in an equation or optimization problem, it's a constrained optimization problem. It's minimize, and we're going to use 1/2 just because the 1/2 is convenient with the squared. Minimize 1/2 norm of W such that, and here's the linear separability condition we stated earlier. So minimizing the norm of W squared such that the data remains linearly separable. And another way to say this is, of all the B and W that satisfy this linearly separable constraint, the one that yields the widest street, and by the street I mean think of this as a street. We want that street to be as wide as possible. The one with the widest street is going to be the one with the smallest norm of W. So that's basically the idea. This thing is called the hard margin classifier. And it's pretty easy to describe based on, these pictures we've been drawing. Okay, so one of the interesting things about this is, and again, this is just, you can kind of see this visually, is that where you place this boundary is actually going to be determined only from a very few samples in your data set, which are the ones closest to the boundary, right? Like in this particular case, these 3 samples completely determine where I put my boundary. All these other ones, like if I move them around, the boundary doesn't change unless I move it so that it's in the street, right? But if I move them around such that these guys are still the 3 closest, the boundary is completely fixed. So this classifier is focusing exclusively on these samples most difficult to classify and ignoring all the rest of them. Okay, so we'll revisit whether that's exactly what we want to do, or maybe it's a little too risky, but that is what it's doing. And these few samples that determine the boundary have a special name. They are called the support vectors. So the boundary depends only on the support vectors. Okay, so those are the main ideas. Any questions about that? Yeah.
Is this specifically for classification?
Yes. Yeah. There is a way you can extend these ideas to regression, but it's easier to understand in the classification framework, and it's much more commonly used for classification. Okay. So the story seems nice so far, but the trouble is that the way we formulated the problem is so far that this formulation of the hard margin classifier, this requires the data to be linearly separable, right? Because we're setting up this optimization problem such that this must hold true. And if this doesn't hold true, you would say there was actually no solution to the problem. So this is kind of, it's a good idea, but it's just limited in scope. Okay, so we have a way of fixing this. That's what we'll talk about next. Any other questions on anything so far? Okay. All right, so the way we fix this is we will replace the hard constraint. This was the hard constraint, which is our linear separability constraint. We're going to replace this with a cost term. So the first thing to realize is that I can rewrite this hard constraint just by moving this term to the right side, which will leave a 0 there. I can rewrite this as follows. 0 is less than or equal to 1 minus this other stuff. Okay, so remember that if the data is linearly separable, this inequality will hold for all your training samples, okay, which means that these guys here will be 0 or less for all your training samples. So the cost term we're going to use is this guy here. So let's think about this. We said that if our data is linearly separable, all these guys will be negative or at most 0. In that case, so this maximization is looking at, it's taking the maximum value of either 0 or this term. So if the data is linearly separable, then for all the different I, this term is 0 or less. So when you take the maximum, you get 0. And you sum that up for all the I, and you get 0. So basically, when the data is linearly separable, then by minimizing this cost, making it equal to its smallest possible value of 0, that's the same thing as ensuring linearly separable data, right? So we're replacing the constraint with a cost, such that minimizing the cost is going to satisfy the constraint. But what's nice about the cost is that it's more flexible. If the data is not linearly separable, if there exists no in B and W such that this holds true for all I, you can still minimize the cost. And maybe what you find is that, the very smallest cost value you get, it's going to be positive. It's some number, it's not 0, but at least you can find the B and W which minimize that. And so you're going to be doing something very similar to, we're still going to be maximizing the margin and everything. It's just that what can happen is that we could have some of these points falling maybe in the street, maybe on the wrong side of the street, and so on. But the ideas are all going to be, the basic concept is still preserved. So again, we're taking this idea, we're replacing this with another cost term that will add to this. So finally, we get the original cost plus this new term from above. And one other thing is we're going to scale this new term as a way of trading off between these two terms in the cost. So we have to figure out how important is it for us to try to prevent any violations of the margin, right? Because when you violate the margin, this thing gets bigger. Are we more concerned about violations in the margin, or are we more concerned about the norm of W being small? So we can choose C to balance between these two terms. if we use a large value of C, that is going to weight these more, and it will make us focus more on this first term and less on the second. On the other hand, if we use a small value of C, it means we'll focus more on the second and less on the first. Okay. So in particular, larger C means penalizes violations more, so we don't want samples to be in the street or on the wrong side of the street. And it allows us, so if we focus on this, that means this will grow larger. And if this grows larger, actually that means that the margin itself is smaller. So it's kind of like you're making the street smaller in the hope that less samples are falling in the street or on the wrong side. But if you, you could go the other way. You could say, I'm going to allow samples to fall in the street. I don't care so much about that. And I'm going to increase my street width proportionally. And that will increase the width. The margin is basically the width of the street. So this is a trade-off that we will have to make. But that's essentially our new classifier. So C trades off between margin size and number of margin violations. And this is a very useful classifier because it does not require the data to be linearly separable. Okay, so here's some illustrations of different values of C. So this is C equals 1,000, C equals 10, C equals 0.1. So when C is very large, in that case, you really don't want samples to violate the margin. So if you look at what's happening in this left picture, the support vectors are circled. So from them, you can basically deduce the street. The street is like here. And you can see the street is very narrow. And the circled, the support vectors are the ones that are either on the boundary of the street or in the street or on the wrong side of the street. So those are the circled ones. Now, as you decrease C, now you can see the street has grown a lot wider. So in this sense, this 1 over norm W is making the street wider. Consequently, more of your samples are violating that margin. They're in the street or on the wrong side of the street. And if you take this to a larger extreme, here you can see the street has grown very wide. There's only a few samples that are not support vectors. Okay. So you might ask, well, how do we decide among these? Or another question is, why is this not the best idea? So let me try to explain why it's not the best. So notice here that there's only a few training samples in your training data set that are actually being used. So when we studied the bias variance trade-off, we learned that there's bias and there's variance. So variance tells us, so we want variance to be small. And one way to think about variance is think about what changes as you go from one experiment to another. So imagine that I do this experiment once and I draw these points and my boundary lands this way. But now I can somehow imagine I can do this experiment again, and I'll have a different random selection of red and blue points. And when I do this again, my boundary will again change because that boundary is really dependent on only the few points closest to it, and those few points will change quite a bit from experiment to experiment. So what that means is you have a high variance. If you do this experiment many times, you'll see that boundary moves around a lot. On the other hand, here I have a much wider street. There's many more samples contributing to where that boundary is. You could say that the boundary is kind of like an average of where those samples are lying. And so because there's more samples there to average, there's less movement in the boundary from one experiment to another, therefore less variance. And as we go to the right, there's even less variance here. That boundary is going to be very stable across experiments. Won't move hardly at all. Okay, so basically, as you go across this way, your variance increases. Now let's talk about the bias. On the left, if you look closely at the color, the pink region look at the pink region and the color of the red samples. It looks like maybe all the samples are being correctly classified, or maybe this one is not. Maybe the blue is in the pink region. But overall, very few samples are in error. You could say is a low bias. On the other hand, in the next picture, you can see that all of a sudden these red samples are being misclassified and these blue ones are being misclassified. And so our bias is growing. And so what's happening is that boundary is tilting right. And over here, there's even more that are misclassified. So variance is decreasing to the left. Bias is increasing to the right. And as we know, we have to find the best trade-off between bias and variance. So, and we also know how to do that. We do cross-validation, k-fold cross-validation. So the idea would be you would train your SVM, or you train your support vector classifier many times for different values of C, and you would evaluate your classification accuracy on your test folds, and you would eventually settle on the C that works the best. Okay, so this is really bias variance trade-off. So larger C, more sensitive to data points close to the hyperplane, lower bias but higher variance. Smaller C, less sensitive to data because the margin or the street width is larger, but higher bias, lower variance. Okay, so is that idea making sense? So we have this important parameter to tune C when we train our SVM. C, more or less, it controls the number of support vectors. As you can see, as C is getting smaller, number of support vectors is increasing. However, it does not mean that if you take C to infinity, you get no support vectors, because if your data set is linearly separable, not linearly separable, there's no way that you can drive your support vectors lower than a certain amount. Because for all the samples for which it's impossible to separate correctly, all those guys will always be support vectors. And so there's going to be a minimum number of support vectors that you can get if you keep increasing C. So things will sort of saturate, nothing will change. Okay. One other thing I forgot to mention is that, so remember how we were extending that hard margin classifier with a more flexible idea here? Well, it turns out that if your data is linearly separable, and if you choose C large enough, that the solution to this new problem will be identical. The soft margin classifier will be identical to the hard margin classifier. It's basically saying, in generalizing our approach, we haven't lost anything. It's always possible to recover that hard margin classifier with the right choice of C and this soft margin classifier, or support vector classifier. Okay, so yeah, so those are the main ideas about the SVC question.
Is there a way to do this like polynomial instead of linear hyperplane?
Yes, there's all sorts of feature, like with any method that's a linear method, you can always do a nonlinear data warping before you use the method. So that, as we'll see, we'll eventually call that the support vector machine when we do that, when we include that nonlinearity as a pre-processing stage. For now, all the main ideas we can think about in the just with the linear formulation. Okay, all right. Is this making sense? It's probably the most complicated mathematical day of the term, I think, some of these ideas. Any other questions on support vector classifier? Yeah.
So you're saying in the cost function, when we increase, when we're trying to minimize the W, it is basically making our classifier more strict.
Well, okay, we're minimizing this, which is minimizing the norm of W, but it's also minimizing this. This is kind of measuring how many violations of the margin we have. So it's kind of, and this is controlling the width of the street. So they're sort of working together.
W are the weights, right?
W are the weights in our classifier, exactly. Yeah, we have the weights and the bias or the intercepted design.
So that's what I want to understand. How is changing the weights actually making the width, adjusting the width of
Yeah, that part's a little bit tricky, I guess. It comes down to sort of this equation. The first thing we figured out is the distance between a point and the boundary. You know, we got the equation for that. And then we added this sign correction. And then after that, we realized that under this linearly separable constraint, it's simplified down to this. So this is sort of the equation that tells us that this is the sign-corrected distance of the ith point to the boundary is greater or equal to 1 over the norm of W. So that's kind of where the idea appeared. So this is our gamma, this is 1 over norm of W. And so, but what's complicated is it's coupled with the idea of linear separability. So it's sort of like saying, if I consider all the ways I can make a linearly separable classifier, so I could put the boundary here or here or here or so on, right? I could move that around. And if you measured the norm of W for all those different choices, you would find that the smallest norm of W or the largest inverse norm of W would be attained right when this is in the middle, equally distanced from both sides. So that's what's happening. It's like if you could somehow have like a little demo where you could move things around and look at the norm of W, that's what you would find. When you put it so that the street is widest, that is when the norm of W gets the smallest. Yeah, so that's kind of what I was trying to say here. Of all the W and B satisfying that linearly separable constraint, the one with the widest street is also the one with the smallest norm of W.
If the targets for classifying, you have 3 or 4 features, it won't be the 2-dimensional. So we can
So-
find the
yeah.
line
So-
for that portion, at least 2-dimensional. But
So remember that the way we handle non-binary classification is to come back to binary classification. So we had the one versus rest method, where we make a set of linear classifiers, like is it in class 1 or not? Is it in class 2 or not? Is it in class 3 or not? And then for each of those binary classifiers, we could still use this method. So that's essentially how it's done. There was another approach called 1 versus 1, where you looked at all pairs of classes. So if you had 3 classes, you'd look at 1 versus 2, 1 versus 3, and 2 versus 3. And then you would design those 3 classifiers. That's actually how it's implemented in sklearn. The support vector machine with several classes. But it is based on binary classifiers at the end of the day. So all the things we're talking about here are directly relevant to that problem. It's a good question.
So the yi, is that just to get it from 0 to 1 to -1 to 1? That's how it's doing?
So in all of our formulation today, just for easy notation, yi is either 1 or -1. So the sign, it's basically doing like a sign correction of this score. So we expect, or we want the score to be positive for when yi equals 1. We want it to be negative when yi equals -1. So therefore, the product of the score and yi, we always want to be positive. You could redo everything for yi equals 0 or 1, but notationally, it's much more cumbersome. Okay. Okay, great questions. Any more questions? Okay, so one thing we could do is we can compare this to something we already know about, which is logistic regression. How does this compare to logistic regression? What is different? So to do this, let's rewrite logistic regression like this. So this is the logistic loss, or you could say the cross-entropy loss, binary cross-entropy loss that we derived before. And this is the particular case where yi is 1 or minus 1. And remember that we tend to use it with L2 regularization because we notice that if you don't have this term and your data is linearly separable, then minimizing this alone will tend to make your weights and your bias go out to infinity. Because the larger you make those numbers, the smaller, actually the more negative you can push that loss. So by adding this in there, this is the common thing, this is used by default in sklearn, you can prevent the weights from going to infinity with linearly separable data. Okay, so this is basically that approach. And like in ridge regression, we always have to have some parameter that weights this regularization term. So when we first studied it, we had something like gamma, or maybe it was lambda. But for some reason, in sklearn, for the classifiers, they use an inverse regularization strength. So, the larger C is, the less weight there is here. Okay, so that's what we know from Unit 5. And what's interesting is we could write our SVC exactly the same way. So all I'm doing compared to the last time we saw it is I'm just going to be calling this ZI, and I'm going to divide everything here by C, because that won't really affect the minimization. So the C will move over here. Okay, so when we have that, we get this expression, and now we can make a direct comparison between these two. Notice that these terms are identical. The difference is that this thing here, the logistic loss, is being replaced with this thing, which is known as the hinge loss. And to make more sense of it, we can plot these guys. Okay, so the logistic loss is this smooth red curve, and the hinge loss is this piecewise linear blue curve. So as we already discussed, and we're plotting this versus YIZI versus this sign-corrected score. So as we already noticed, when the sign-corrected score is 1 or greater, we're happy. We place absolutely no penalty on that sample. So here you can see the penalty is 0 for all these values. On the other hand, this point, when we're right on the boundary, when this thing equals 0, that's when we're right on the edge of the street. And as this quantity grows negative, that means we start to be in the street, and this term just grows linearly from that point on. Okay, so the farther it is from the good edge of the street, the bigger and bigger weight we place on that sample. So that's reflected by this line. Okay, so that's what's known as the hinge loss. On the other hand, logistic loss, you can see it actually looks quite a bit like the hinge loss, but it's a smooth approximation. You can show that asymptotically it has exactly the same slope, and it converges to 0. But what's interesting about it, and what's different than the hinge loss, is that the loss never goes exactly to 0. It's always a little bit positive. It gets small, but it never goes to 0. So whereas the hinge loss, or the SVC, places no penalty on samples that are obeying the margin, the logistic loss penalizes all samples. In other words, even the ones that are easy to classify, it is somehow saying, I don't like that one. I'm going to give it some loss. And this is sort of related to that experiment we saw with MNIST, where we noticed that with a few samples, logistic loss, logistic regression seemed to be giving us weights that made sense. But then as we use more and more samples, the weights started to get kind of weird. And maybe it's because it's placing emphasis on a lot of training points that are really easy to classify. Maybe you should just focus on the few hard ones. That's what the SVM will do. The focus is on just the hard ones, doesn't get distracted by all the easy ones. And those hard ones, the ones it's going to use, those are called the support vectors. In terms of an equation, those are the ones whose sign-corrected score is less than or equal to 1. Okay, so that's a way of connecting SVC to something that we're already familiar with. All right, so that's a good place to stop for today. If there's any other questions, please come and see me after class. And have a good fall break. I'll see you guys on Monday.